Yeah, good evening, everyone. We'll start in 1 or 2 minutes. Exactly at 6:05 we'll start. Yes, Shanti, have you solved the last week assignment problem? Did you get the correct answer? There was a question of Fe3 plus and Ta3 plus. A3 plus or 4 plus, I don't remember. Would you be able to solve that? Am I audible? Yeah, this week, what we have seen in the lectures are two type of things. One is the transport number calculation, and second one is the conductance, conductivity, resistance, history, all those kind of stuffs. So before going into that, since some of you asked questions regarding last week's one homework, so others, Hamalada, Smita, all of you able to solve that question that what is the potential of 0.01 molar Fe3 plus that question? Did you all get correct answer? Assignment 4. Yeah, sure. So I just solved it. I'll just work it out here. What was the question? So initially we'll see one problem, that assignment problem, plus one more similar problem I will solve for you in the class now. So try to solve it with me. We'll from where you are not getting, we'll start from there. So question is, what is the potential in 0.01 molar Fe3 plus solution titrated 25 percentage with 0.0112 molar Ti3 plus. Ti3 plus or 4 plus, I don't remember. It was 4 plus, right? 4 plus or 3 plus. Ti4 plus, I guess. Yeah, given E0 Fe3 plus bar Fe2 plus is equal to 0.77 volt, and E0 Ti4 plus bar Ti3 plus is equal to 0.13 volt. How you can solve it? Anyone got the answer for this question? Only three of you are joined. So any three of you? Yeah. Any of you got the answer for this question? Last week assignment. Yeah, answer is 0.78 volt. So are you able to solve it? Okay. So this is a titration actually. So as you have already seen in the class videos, during titration there was one more probe was inserted which was showing the potential in that one, right? So this is that kind of problem. So we can solve easily. E is equal to E0. Before that I'll write the reaction. Fe3 plus electron gives Fe2 plus. So how can I write the next equation? E is equal to E0 Fe3 plus bar Fe2 plus minus at 25 degrees centigrade. 0.0591 divided by 1 log of concentration of Fe2 plus divided by concentration of Fe3 plus. Right. So what is given? What is the potential? Solution is titled 25 percentage. So it is like Fe2 plus is 25 percentage, Fe3 plus is 75 percentage. So we can directly write it is equal to value of E0 is given 0.75 minus 0.0591 log of 1 by 3. So if you calculate that value will be coming 0.793 volt. So in that option, the value which is coming close to this is 0.78. So that may be the answer. It is actually a titration. You don't need to take a full cell reaction or anything. So it is a direct answer. You know, because these potentials are given to understand whether it's an oxidation or reduction reaction. Whether oxidation or reduction happens at Fe2 plus Fe3 plus. So that's a indication which is given. So like that you'll get. When it's a multiple choice question, it is easy. You can, when there is no other answer close to 0.793. So I'll choose 0.78. TA3 plus is TA4 plus is a titrant, but here we are not asked to find out what is a cell. This is not a cell, it's a titration like thing. So I think you also notice while doing the titration in that videos there is potential also varying. It's a single probe like thing. So here just to understand whether oxidation or reduction, when we couple these two, oxidation or reduction take place, that's it. So that really before also one question we have seen E cell was given, but we were taking from literature and solving the chlorine problem. So like that here for this problem, we doesn't need that value. So one more thing, it was asked from where to where electron flows during. So I have consulted with many people. For my answer was also like electron can flow from anode to cathode only through external supply, whether it's electrolytic or what you say galvanic mode because at cathode electron is getting consumed. So I'm also not sure with the answer given in the assignment solution. Hmm. Yeah, so you may have to ask to the professor. So for me also the answer looks like wrong, not correct, because electron can't be flowing from cathode to anode because at the cathode electron is getting consumed. So that question framing is maybe I thought like maybe some conventions or something. Anyway, understand this. At cathode, electron is getting consumed. At anode, electron is getting released. So in a galvanic mode, it's pretty straightforward that electron need to come through the external circuit and get into the cathode where reduction happens. Here we are forcefully giving electron by an battery or some supply. So electron flows here, electron consumed, but electron can't go from cathode to anode. That's what my understanding is when I consulted with one from some faculties also. They shared the same idea. So I hope from my side the answer is clear. So please write regarding that question. Yeah, we'll solve one similar problem, whatever we have seen just now. So write down the question. Question. A solution contain 10 raised to minus 3 molar Cr2O7 2 minus. Yeah, today we will be solving multiple number of transport number problems. No, don't worry. So initially, I'll just because last class there was some, actually what happens is last class there were some doubts on this particular question. Since the assignment was not submitted, I put it for this week. So after only one extra problem I solved, then we'll go to little bit of theory. I'll refresh the transport number calculation methodologies, then conductivity measurement. Not too deep, but I'll just brush up it. Then we'll see multiple number of problems regarding conductivity as well as what you say transport number. I'll also show how the transport number regularly in our lab we calculate. So that's also for additional knowledge, not for exam point of view, but how a lithium ion battery using a polymer electrolyte, how we can calculate the transport number. That also I will show with the example problem. Okay, solution containing 10 raised to minus 3 mole Cr2O7 2 minus and 10 raised to minus 2 molar Cr3 plus if the pH of the solution is 2, what is the potential of half cell reaction is given E0 is equal to 1.33 volt. A solution containing 10 raised to minus 3 Cr2O7 2 minus and 10 raised to minus 2 molar Cr3 plus. If the pH of the solution is 2, what is the potential of half cell reaction? Given E0 is equal to 1.33 volt. So can you try to solve this one? So for easiness, I will just write the equation. From there, it will be very easy. So we'll just pass it. Cr2O7 2 minus plus 14H plus 6 electron is giving 2 Cr3 plus 7H2O. So half cell reaction I have written. So from here, you can take the Nernst equation and try to solve this. How will we start? E cell is equal to E0 Cr2O7 2 minus plus Cr3 plus minus 0.0591 divided by 6 log of concentration of Cr3 plus square divided by concentration of Cr2O7 2 minus into concentration of H plus raised to 14. So concentration of H plus, how can we get? We have pH is equal to minus log of H plus concentration. pH is given. So 2 is equal to minus log of concentration of H plus. So you can take like, so you will get H plus concentration of 10 raised to minus 2. So concentration of H plus will be equal to 10 raised to minus 2. Now we can substitute here. Is the step clear? Any doubt? Once you can write this equation, it will be easy to solve, I think. But you have to crack this equation. Okay, sure. So just substitution now equal to 1.33 minus 0.059. If someone is solved, they can put the answer in the, since it's straightforward. Log of 10 raised to minus 2 square divided by, it won't be a square bracket, 10 raised to minus 2 square, and 10 raised to minus 3 into 10 raised to minus 2 whole raised to 40. So we just solve it. So it will be 1.33 minus 0.0591 divided by 6 into 27, which is nothing but 1.064 volt. Yeah. So now we'll move on to the last week's portion. I'll try to go it little faster just to give a brief idea what we have seen. If you are clear with that, which one? 27 or 23? Let me see. It's 10 raised to minus 28, 10 raised to minus 28 plus 31, 31 minus 4. Uh, yeah, 31 minus 4, it's 27. Yeah. So last week's classes was mainly revolving around first topic is the transport number calculation. So what happens when a potential difference is applied to an electrolyte? Ions may move. Cation moves towards the negatively charged one electrode, and anion moves towards the positively charged ions. The total charge released at the cathode and anode are equal. eh, Equal, and function of total current carried by cation and anode general are not equal. Okay, so the concept is whenever we apply, so what happens is we have a cell which is at OCP. Whenever we put a small disturbance, cations and anions. So cell contains cations as well as anion. So how a cell look like? So here we have a positively charged one. Here we have a negatively charged electron. So whenever we apply potential, the electrode is also possess some charge. According to that, the negative charges will polarizes and moves towards the positively charged electrode, and positively charged ions will move towards negatively charged electrode. So this movement will be depending upon multiple factors. So what happens? Sometimes what happens? There will be two type of. Suppose we take HNO3. So here uh, the transport of ions will be depending upon multiple factors. One is one factor is what is a charge or number of charge and number of what is a number of charge or concentration, and it will also depend upon, as we have seen already in the liquid junction potential, another terms called mobility of ions. So we have seen in the class, for example, in HNO3, only 18 percentage of the mm, current is taken by NO3 minus, whereas 82 percentage is taken by H plus. What is the reason? As we have already seen, it has very high mobility. So when we took three examples, which was H plus is to K plus is to Cl minus, the ionic mobility was in the range of 374 is to 76 is to 74. So similarly, we have seen some other example in copper sulfate solution. 38 percentage of the current is taken by copper, whereas 62 percentage is by SO3 2 minus. So there is a relationship. As you can understand, there is a relationship between ionic mobility and the transport number. Or transport number is a measure of the fraction of total current we are applied, that may be I, which is taken by anion and taken by cation. Sometimes it can be 50, around 50-50. So this is the reason why we use in salt bridge and all, we use KCl lighting, because here also you can see its ionic mobility is in the close proximity. So we'll try to find how the transport number is generally represented. So we'll take a solution in which n plus number of cations per unit volume and n minus number of anions anions per unit volume. Let Z plus be the charge carried by cation, and Z minus be the charge carried by anion. Similarly, let's oh okay. Let I be the total current, and E be the unit charge. Hmm. So we will consider a unit cross section, unit cross and we apply a current for a time of 1 second. So when we apply a current, whatever electron which is in a proximity of 1 centimeter can come and get reacted at the electrode surface. So we can write a total number of cation discharge at cathode will be equal to n plus into u, where u is the mobility of cation and v is the mobility of anion. Similarly, total number of anion discharge at anode will be equal to n minus into v. Then since we are applying a current, there will be a charge which will be carried by anion and cation. So it will be distributed. So total charge conducted by cation will be equal to, what will be that, n plus u into Z plus into E. Similarly, total charge conducted by anion will be equal to n minus u into Z minus into E. So we have to maintain the electronic neutrality. So for that, what is the condition? So whatever anions getting total number of total charge getting discharged at the cathode should be equal to total charge getting discharged at the anode. So we can apply that n plus into Z plus should be equal to n minus into Z minus. So we will apply this. Before that, we will calculate total current will be equal to I plus I minus, which can be written as n plus u into Z plus E plus n minus u into Z minus E. So when substituting this into this equation, you can write, how can you write? It will be I is equal to n plus Z plus E into U plus V will be the total current. So now what is the transport number, as we already mentioned above? So transport number is the ratio of, can be the total, what is the total applied current? In that, a fraction of current will be taken by cation, a fraction will be taken by anion. So we can write T cation will be equal to, we will represent T plus U divided by U plus V. Similarly, or we T minus is equal to V divided by U plus V. Then we have total transport number will be equal to 1, t minus equal to 1. So you can also write from here t minus is equal to 1 minus t plus. So this is a general outline of how we can calculate the transport number. So as a general, we can write this is you can remember for doing problems. So I'll define as transport number of equivalent lost from anode chamber divided by total total number of number of equivalent lost from two chamber, which is nothing but u by u plus v, which is nothing but t plus. Fine. This law is, what is this law name? What is this law called? The you have learned in the week class. What is this law called? Kirchhoff's law. So is this derivation clear to everyone? In that case, I won't be doing the derivation for the next part. Experiment. Next part is the transport number, experimental determination of transport number. So in that, sir has showed two type of things in the class. What are they? First one is one setup. So first one was we have two containers, two cells, two compartments. First compartment is like this. Then from here we have an electrode, which is nothing but 0.1 molar CuSO4 A, B, then C we have another electrode C. Here we will connect it through a ammeter and a coulometer. Then it will go to a battery where negative is connected here. Negative positive, negative positive. It is then connected here. So what happens? We will apply current for a short time. Then take the solution out using iodometry. We'll find out what is the copper 2 plus present. So from initial and final weight, and using the this coulometer, we will calculate what is the total charge. Using that, we can calculate the transport number. So transport number will be coming T plus is equal to Z minus X minus Y divided by 159.6 divided by Z total charge. This also in terms of charge we are writing. So for a second we are passing current and deriving what's the transport number. So is this method clear to everyone? So weight we have to take, it's basically weight change. So initially there will be a 4.1 molar copper sulfate. After applying current, we'll take out the solution. Suppose from here it is W1. So which contains W2 of Cu2 plus. Using that we will be. Similarly, coulometer have a weight change of W3. Using the equivalent weight and all, we will be deriving this equation. Is that I think the derivation was straightforward and clear in the classes. So second one is the moving boundary. Am I writing those things? Moving boundary method. Yeah. Second one is moving boundary method. Here, what's the setup looks like? So it was like this. You can here also you have some setup like this. Then here you have a platinum cathode, and here you have a cadmium anode. Then you will connect it to a battery, negative, positive, negative. Then through a resistor, it will go. From here, you will go through a coulometer, copper or silver platinum coulometer. Then from here, through an ammeter, so it will like a jockey like thing will go here. So here two type of solution separated by another solution. You can see here this portion is filled with CdCl2. Here it is filled with HCl. Here it is filled with CH3COOH. You can see here the anion is common. So you can name it as M A dash. This is M A. This is M dash A. Is that clear? So this in this type of moving boundary method, the cation and anion chosen like that. Here M A dash, then M dash A, then we have a solution M A. Here we have a common common cation. In this two system, we have a common anion. Here you can see here the anion H plus mobility is higher than Cd2 plus mobility. Okay. Similarly, Cl minus mobility is higher than CH3COO minus mobility. So what happens when a potential is applied? H plus will move faster than Cd2 plus, and the boundary will move upwards. So it will move up to a new boundary called Z dash. Using that, we can say if it, I will write that portion. If Q is the quantity of electricity used, I will find it out by the coulometer. Then the fraction of charge transported by H plus, how it will be written? T plus into Q. Similarly, you can write T plus Q gram equivalent of H plus mode implies as T plus Q is equal to L A C divided by 1000. From this we can write T plus is equal to LAC divided by 1000 Q. This is how we write with moving boundary, where LAC is the amount of HCl moved up. Suppose we take a uniform cross section of A and it is set apart by a distance, moved up by a distance L. We can write, suppose the concentration of HCl is C molar or C equivalent molar. So we can write the amount of HCl moved up is equal to LAC divided by 1000. So this is the way how the transport number. This is a direct straightforward equation also. The transport number is equal to LAC divided by 1000 cube. So these two methods are clear. So I just want to give you a flavor. So I am going a little faster in this region because you all have seen this portion in the classes. But this is, this is not for exam. I just want to show. So in laboratory and all, we used to calculate transport number. So what is transport number? Transport number, which tells about the contribution of a particular charge species present in the electrolyte to the overall charge transport across the cell. Overall charge transport to the charge transported by a particular anion or cation. So here what we are trying to do, we are trying to find out transport number of Li plus in a lithium ion battery. So Li plus transport number in a polymer electrolyte has been estimated using a combination of something called electrochemical impedance spectroscopy and a polarization measurement. Just for this is a technique. If you don't know, don't worry. This is not gonna come for exams. So impedance spectroscopy and polarization. Polarization is nothing but we will apply a constant potential for a longer period of time and we will see what is the uh, current response. So for this, we have used a lithium plus symmetric cell. Uh, like here, anode as well as cathode is a lithium. In between, we have a membrane. So what we will do? Oh, sorry. So initially we will do a impedance spectroscopy experiment. So So what happens in this process? So here, when we apply a potential, both cation. So initially at OCP, since it's a symmetric cell means anode and cathode are lithium disk. So what will be the open circuit potential in this case? When two metals are same, what will be the open circuit potential? So what will be the open circuit potential? Zero, correct. Sorry about it. The picture is not coming here, so I'll try to open up the presentation directly and share from here for a minute. Is my screen visible now? Is my screen visible? Can anyone hear me? Hello? Okay, okay. Sorry about it. The picture didn't come in the converted form. Yeah. So I can't write here, so but we'll manage. So what happens is when we apply a small potential of suppose 10 millivolt, what happens? Both anion and cation started moving. But what happens because an anion for oxidizing or reducing anions, we need a higher charge or higher current. So it cannot undergo any changes. But lithium plus will go undergo oxidation and reduction at the cathode and anode. See, so what happens therefore? What After some time, uh, since anion cannot undergo any changes, it will get accumulated at one of the electrodes. So, in order to neutralize, the cell should maintain the neutrality. So, cation, so this lithium plus in the electrolyte will try to move towards the electrode and try to neutralize it. So, as you can see here, initially the current is I0 value, the value of I0. So initially when we apply 10 millivolt, it started decaying over time. It slowly goes and comes to a steady state. So what happens at steady state? The cation, anion, they understood they won't get oxidized or reduced. So as it neutralizes, it stop moving towards the electrode. So in this all regions from here to in all these regions, both cation or anions are transporting charge, whereas once the steady state is reached, only cation, that is lithium plus, is transferring the charge. In this case, what is the transport number? Transport number is nothing but charge carried by cation. For transport number for a cation, charge carried by cation divided by total charge. So in this case, we can write ISS divided by I0. But there is one more problem. As you can see, lithium and the electrolyte also contain some active species. So it can also, what you say, consume some sort of lithium. So it we should the consumption of lithium will leading to a change in resistance. So that need to be incorporated also for the calculation of transport number, because some of the lithium is gone somewhere because of reaction. So for that, we'll calculate. This is technique is called electrochemical impedance spectroscopy, which will give the bulk resistance. So for now, just for understanding, I'm saying this. So then we have the initial current and steady state current. Then we will be having initial resistance as well as steady state resistance. So there is an equation called, I'll write it in the paper. It's called Bruce Wilson. So equation is also not coming. So I'll write it down. So there is some equation called Bruce Wilson. Bruce, Bruce, Vincent, Evans. We simply call it Bruce Wilson equation, which tells TLI plus is equal to ISS divided by I naught. Then in order to eliminate the effect of lithium being consumed at the cathode or in the electrode, sorry, in the electrolyte, we will take the resistance value also divided by delta V minus ISS minus into RSS. So using this equation, we can in the laboratory we can find out what is the transport number of lithium. So in this example from the experiment we got the values, and we can calculate the transport number to be 0.5 0.5. So remaining transport current is carried by anions. Is it clear? So I just shared it, so don't worry about it, this is not in syllabus. So I just wanted to show, give a flavor how the laboratory experiments are really done. Now I'll share from here again. So these are the experimental methods to determine. First one is using the weight loss experiment. Second one was the moving boundary method. This is not in syllabus, but it's both knowing it. Its method is called Bruce Vincent Evans method for calculating the transport number. So we'll move on to the next topic, which is relatively very easy, and you can expect more problems to come from this portion. So we have something called resistance, resistivity, conductance, gamma, then conductivity L. So what is resistance? Consider a metal of unit of, not unit length L and cross-sectional area A. So resistance R is equal to rho L by A, where rho is the resistivity or specific resistance. What is the unit of resistance? What is the unit of resistance? Ohm. So it is represented by the Greek letter ohm. Sorry, my ohm got to ohm. So from this equation, you can write rho is equal to R A by L. So resistivity is nothing but resistance of a substance of unit cross section and length. So when A and L are 1, you can write rho is equal to R. So similarly, we have what is the unit of resistivity? It is ohm centimeter. Then now we have some other quantities which are conductance gamma capital gamma, lambda, which is given by capital lambda, which is given by 1 by R. So its unit will be ohm raised to -1. People will say mho, or I'll specific Siemens. Then next term is specific L specific conductance, or simply we'll say conductivity, which is nothing but 1 by rho, which is inverse of this. So how can we write the unit of this? We can write, what is the unit of conductance or specific conductance or conductivity? What will be the unit? It will be Siemens centimeter raised to minus 1, or more centimeter raised to minus 1. It is just the inverse of, we have it written here, ohm centimeter. So 1 by ohm centimeter, which will be more centimeter raised to minus 1, or Siemens centimeter raised to minus 1. So we can, here also we can write specific conductivity is the conductance of a solution of solution enclosed between electrodes of unit cross section and kept 1 centimeter apart. Unit cross section, you can say 1 centimeter square. So here I want to you to note one thing. The conductance is function of two things. First one is number of ions present in the solution, as well as concentration of the solution. I'll ask a question from this. So for if you want to compare the conductance of or specific conductivity of two systems, we have to take into account the concentration. So we need to have some normalized way of representing it. This is done by uh, something called equivalent conductance, or sometimes we'll be seeing in problem molar conductivity. So it is the conductivity of 1 mole of solution, one of a 1 molar solution. Simply we can say. So if we say 1 gram, if we have a solution which is 1 gram equivalent per liter, then the volume of solution will be equal to 1000 divided by C, which is in centimeter cube. We can write lambda is equal to A by L into L, which is nothing but 1000 divided by C into L, where L is the conductivity or specific conductance. So this is an equation we have to use. So we can write lambda is equal to 1000 by C into L. So this is a direct equation. Here, what are the L is equal to a function of concentration and temperature. So in the textbook, I think sir has given some values. What are they? Like for a KCl solution of 1 normal, 0.001 normal, 0.005 normal, etc. like that. What are the values of at different temperature also? Some Kohlrausch and workers determine the value of specific conductance or conductivity of pure KCl solution. So that values will be useful for solving problems. Similarly, we can have some more relation like L is equal to, then we will define one more thing, which is nothing but the cell constant. So we have written capital lambda is equal to A by L into conductivity L. So when we rearrange it, we will easily get it. So we will define one more thing, L by A, which is nothing but cell constant, which will define determined by capital K. What is the unit of cell constant? What will be the unit of cell constant? What will be? Centimeter raised to minus 1. Yeah. So when we just rearrange it, we can write L is equal to K into lambda. So K is equal to L by lambda. So 1 by lambda is nothing but resistance. So K is equal to L into R. So we have many relations here which can be, if you remember directly, you can directly solve the problem. So theory, I think it's enough for today. So let's do some problem. We'll start from the problem which is sir asked to solve in the class. What was the question? At 18 degrees centigrade, the resistance of 0.1 normal KCl in a conductivity cell is 86.8 ohm and 0.05 normal NaCl is 203 ohm. What is the equivalent conductance of NaCl at 18 degrees centigrade? NaCl 18. 18 is already given. So can you try to solve the problem? So that's why from the table given in the class, we can write at 18 degree centigrade, we have for 0.1 normal KCl, we have L is equal to 1.1192 into 10 raised to minus 2 Siemens centimeter raised to minus 1, or you can get more centimeter raised to minus 1. So from here, can you calculate what is the equivalent conductance or molar conductance? Equivalent conductance. In this case, it's given in normal, so we'll stick to the term equivalent conductance of the 0.05 normal and NaCl solution. Once someone solves, just put solved. We'll give time for others also. Done. It's a straightforward question. How can we solve this? Are you able to solve, or shall I solve the first question? Are you able to solve? Okay, let's start solving this. In the last page, we have given there is something called cell constant. cell constant K is equal to L into, okay, solved, okay. So K is equal to L into R. Here we know for the first solution, point 0.1 normal KCl, we know the value of L as well as we know the value of R. So we can write K is equal to 86.8 into 1.1192 into 10 raised to minus 2. So what will be the value? What will be the value of cell constant? What will be the value of cell constant? 0.971 centimeter raised to minus 1. For a particular cell, the cell constant won't vary. So how can we find the conductivity, specific conductor or specific conductance or conductivity of NaCl? Concentration I am not writing is equal to, again the same formula we will apply, K by R, which is nothing but 0.971 divided by, what is the value given? 203. So what will be the value? It is 4.78 into 10 raised to minus 3, ohm raised to minus 1, centimeter raised to minus 1. So it is Siemens centimeter raised to minus 1. So now we have the value of L. From L, how will we find the value of equivalent conductance? Equivalent conductance. So we have small lambda is equal to 1000 L divided by C, which is nothing but 1000 into 4.78 into 10 raised to minus 3 divided by 0.05, which is nothing but, what's the answer? Yeah, 90. What is the unit? What is the unit of equivalent conductance? Unit also I need. Otherwise, if I am evaluating the paper, I won't give mark. Yeah. So ohm inverse mole, here actually it's given normality. So you will get gram equivalent. If it is molar conductivity, it will be mole. So we'll do another problem like that. So don't worry. So is it clear to everyone? It's easier, right? So we'll apply the same methodology and do another problem. Question is the conductivity of 0.2 molar solution of KCl is 0.0248 Siemens centimeter raised to minus 1. So I will write it a ohm inverse centimeter raised to minus 1. Calculate the molar conductivity represented by lambda m. So calculate the molar conductivity of the solution. But how can we solve it? What's the answer coming? What is lambda m? Okay, someone already commented. I didn't see. Sorry. So for others, I'll just solve. Answer is 124. What is the unit? I can't see the unit here. So lambda m is equal to 1000 L by C, which is nothing but 0.0248 into 1000 divided by 0.2, which is nothing but 124.01 Siemens centimeter squares per mole. Actually, in the last problem, it was normality was given. So it will be gram equivalent. Here it's molarity is given. So molarity is nothing but mole per liter. So actually that 1000 value is coming to convert the liter into what you say centimeter cube, because the unit of L is in centimeter. That's right. Here you can see here it's normal. Here it's given in molarity. So it is, we call it molar conduct. Yeah, that's it. So shall we move on to next question? Question is the measured resistance of a conductance cell containing 7.5 into 10 raised to minus 3 molar solution of KCl at 25 degrees centigrade is 1005 ohm. Calculate the molar conductivity and of the solution given cell constant is equal to 1.25 centimeter raised to minus 1. Week 5 is next week. Its due date is not done, right? So week 5 I am not able to. I haven't checked it once. That's one thing. Then if question is not finished, I won't be touching those questions. Probably anyway next week I will explain. But still, the thing is that the answer will come. The direction we got is you should not discuss the questions which is gonna be solved in this week. So that's why even the first question I solved this week only, assignment 4. So here a specific thing you can ask me. I haven't seen what is the question. Okay, but that's also I'll try to clarify next week, because I am also the question is put by the Isar Mohali professor. Two cathode weights are given. Okay. If the question is wrong, you don't need to be worried. So let me check. Anyway, next class starting, I'll try to solve that problem. So now try to solve this problem. After this, we have a few transport number questions. How do we solve this? What's given? Cell constant is given. K is equal to L into R. So we can write L is equal to K by R, which is equal to 1.25 centimeter raised to minus 1 divided by 1005. What will be the value of this one? Conductivity, specific conductance or conductivity. What will be the value? It will be 1.24 into 10 raised to minus 3 ohm raised to minus 1 centimeter raised to minus 1. I will write this as Siemens centimeter raised to minus 1. So now lambda m is equal to 1000 L by C. We know L, so it is 1000 into 1.24 into 10 raised to minus 3 divided by C. What is the concentration given? 7.5 into 10 raised to minus 3. So what will be lambda m? Yeah, lambda m is for me 165.33 unit ohm centimeter squares per mole. Is it clear to everyone? Others? Okay, sorry. The unit is Siemens. Siemens centimeter. It's ohm raised to minus 1, so I'll write it as capital S. Or mho. Both are fine. So the next question. So we'll. I have written some other things. Yeah. Actually, there is one more problem, similar problem from conductivity. Then we have how many? Two problems from the transport number. Two or three problems I will. So the question is, next question, the resistance of a conductivity cell filled with 0.1 molar KCl solution is 100 ohm. If the resistance of the same cell, if the resistance of the same cell filled with 0.02 molar KCl is 520 ohm, calculate 1 conductivity, 2 molar conductivity. Given conductivity of 0.1 molar KCl is 1.29 Siemens per centimeter. Sorry, Siemens per meter. So just see the unit. Can you try to solve? What's the answer coming? So first we have K is equal to L into R. So from that we can find out what is the cell constant, which is equal to 1.29 into 10 raised to minus 2 Siemens per centimeter. I have just converted it to centimeter unit into 100. So which is nothing but 1.29 centimeter raised to minus 1 cell constant. So from here, so what is conductivity? L is equal to K divided by, you can write cell constant R of 0.02 molar KCl, which is equal to 1.29 centimeter raised to minus 1 divided by 520, which is nothing but 2.481 into 10 raised to minus 3 ohm raised to minus 1 centimeter raised to minus 1 or Siemens centimeter raised to minus 1. So please calculate lambda m now. Lambda m equal to you did some mistake somewhere. So what will be lambda m? Lambda m is equal to 1000 L divided by C, which is nothing but 1000. Yeah, it's 124 answer. So 1000 into, I think you have in converted centimeter or something. 1000 into, what is the value of L? 2.481 into 10 raised to minus 3 divided by 0. What is the concentration? 0.02, 0.02, which is nothing but 124.05 centimeters squared per minute. Yeah. So I think all of you got this part. This kind of problems you can expect. I think if it will be twisted a little also, you all can solve it. Like cell constant. For a same cell, if the concentration of the solution is changed, you just need to find out the cell constant and solve it. Like all the relating relations, like what is resistance, what is resistivity, what is conductance, what is conductivity. Those equations all you need to be remembering. Remember one, all other will come on its own. So let's move on to a problem on transport number calculation. A, yeah, you're asking something? Okay. That's why I told someone to mail, right? Because I don't have any idea about it. You can only get this answer from NPTEL team. So in that case, I will also just ask here in IIT Madras. I'll ask the NPTEL team how the exam is conducted. Give me this week. So let me put a reminder myself. So when I go NPTEL office, I'll just ask this. Yeah, I'll just put a reminder. Yeah, I have to check also, right, how the calculator will be. Okay, I have put a reminder, so hopefully I'll remember. So the next question, a decinormal solution of AgNO3 was electrolytes between platinum electrode. After passing current for 4 hours, a fall in concentration of 0.0006224 gram equivalent was observed in anodic solution. The mass of copper deposited in Cu coulometer placed in series found to be 0.04897 gram. Find the transport number of Ag plus. Given equivalent mass of Cu is equal to 31.8 U. So here we have to calculate the transport number of Ag plus. Hope the question is clear. If you wrote the question, so I'll give a clue. We have transport number of cation is equal to number of equivalent lost in solution divided by total number of equivalent lost from, I'll write as chamber, from both chamber. So you have to find out equivalence in of silver lost as well as total equivalence lost. So from that you can find out what is the transport number of TAG plus equal to. Yeah, answer is correct. Yeah. What about others? I'll give like how much? 2 more minutes. Then I'll try to solve it. Here what is given? There is a falling concentration of Ag plus near anode is equal to 0.0006224 gram equivalent. Similarly, mass of Cu deposited is equal to 0.04897 gram. So from this mass, you can find out what is the equivalence of copper deposited, right? Right? Gram equivalent of copper deposited. So gram equivalent of Cu deposited will be equal to 0.04897 divided by what was the value given? 31.8. 31.8. So this much gram equivalent of copper. So what's the value? Gram equivalent of copper. The value will be coming 1.54 into 10 raised to minus 3 gram equivalent. So now what is the transport number? TAG plus will be equal to number of equivalent of Ag plus lost from anolyte chamber divided by, or I can simply write it chamber, you can remove anolyte divided by number of equivalents of Cu2 plus deposited in coulometer, which is nothing but total falling concentration of solution, because in coulometer it corresponds to total charge or current. So which can be written as 0.0006, what was the value? 6224 divided by 1.54 into 10 raised to minus 3. What will be the answer? 0.4042. Is it clear? Everyone clear with this problem? Yeah. So let's move on to next question. Next question is calculate the transport number of Ag plus comma Br minus ions when a current flows through an infinitely dilute solution of AgBr at room temperature. So we'll take it as 25 degrees centigrade. Given ionic mobility of Ag plus and Br minus at infinite dilution are 6.01 into 10 raised to minus 8 and 8.04 into 10 raised to minus 8 meter squares per volt second, respectively. Respectively. So it's a easy question. This is correct. So what about others? So it's simple, like it's given the ionic mobility. So we have taken if ionic mobility of cation is U and mobility of anion is V, we have written T plus is equal to U divided by U plus V and T minus is equal to V divided by U plus V. So initially we just derived it. So here what is the thing? T Ag plus is equal to 6.01 into 10 raised to minus 8 divided by 6.01 plus 8.04 into 10 raised to minus 8. So when we divide this, it will come 0.4278. Either you can do V divided by U plus V, or you can simply write T Br minus is equal to 1 minus 0.4278, which is nothing but 0.5722. Clear? So we'll stop with one more qualitative question. So the question is conductivity of 0.01 molar NaCl is 0.00157. Yeah, Lavanya, you want to ask some question? Okay, no problem. Hey, mho centimeter raised to minus 1. What happened to what happened to conductivity if 100 ml of extra water is added? I'll give option. A increases. The second option is decreases. Third option is remains same. Fourth option is first increases, then decreases. So what will be the answer? Conductivity, whether it will increase or decrease if you dilute, or it will remain same, or will first go up and increases. Yeah. So it's a simple question. So I just want all of you to remember the conductivity is a function of number of ions present and at the same time concentration of the solution. So once the concentration changes, conductivity will also change. So that's why we will go for molar conductivity, lambda n. So I'll stop here, I think, today. So I had covered. So theory portion I rushed a little. So next week I'll, yeah, someone raised hand. Yeah, that's actually coming in next week's lecture. That's why I didn't discuss. So next week's lectures, the point is directly coming. So that's why I didn't. So you are telling about HCl, then KCl, NaCl, LiCl, those kind of increase, right? As we go, the transport number. So that portion is discussing in the next week's lecture. So that's why I didn't touch it up. So that's it for this week. So what we learned this week is one, transport number calculation. What are the experimental thing? One is by loss by using the iodometric titrations. Second one is moving boundary method. Third one, out of not in syllabus, but we can use something called electrochemical experimental techniques such as electrochemical impedance spectroscopy, which is nothing but a measurement of resistance. Resistance won't be a simple number in electrochemical system. That's why we call something like impedance. Then using polarization method like chronoamperometry, we can measure the transport number. Okay, again, hand raise. Yeah. Question paper pattern, I don't have an idea. Actually, uh, probably whatever the assignments, that pattern will be because I'm not a person who wrote this exam. So, whatever the previous year assignments and this year assignments, I'll be formulating questions. Hopefully, that thing you have to write to the professor because I don't have any direct contact with the professor. So pattern, we can expect something similar because whatever teaching only will come because in the assignments also something similar is coming, right? So that you really need to ask. So this one, I think it will come part of that. I'll ask the NPTEL office how it will be the objective one or multi choice questions. Those things I will ask. Then calculator thing. So you told last week to check the calculator. I forgot actually. So I'll check the calculator as well as whether they will allow calculator or not. Those things I will ask and let you know. Now I won't be checking Q5 in it's assignment 5, right? 5, Q5. So next class we'll be solving that first. Like today also we solved two problems in the starting. So we'll solve this problem first. So I'll check and do that next week first. That's it. Second one is straightforward. It is Ohm's law. What we have seen. For a conductor, resistance is proportional to resistivity. Resistivity is the property of the material into L by A. So from that, resistance, resistivity, conductance, conductivity, molar conductivity or equivalent conductance. These terms we have told why it is important. So the if the conductivity is very low, the potential will go. This is something called ohmic drop, which will occur in the solution, and whatever we are applying for happening a electrolytic process, it won't be going to the solution. The entire portion won't be going to solution. Some part will be drop in the solution itself. So in order to avoid that, we'll apply the Ohm's law. We'll increase the conductivity of solution as much as possible. Like that, that application of Ohm's law is very important. So that's what we are seeing here. So we connected it to electrolyte solution and do some problems. So that's all okay. So I think that's it for this week. Next week we'll see with some more problems and theory. Thanks everyone. So I think March half the exam will come, right? So next week itself, if I can gather the information, probably tomorrow itself I'll go and check. Thank you everyone. So see you next week.